All right. First of all, does anyone remember what I said about how to do Maclaurin series yesterday? Let's start from there. Does anyone remember what I said about the series yesterday? Raise your hand if you still remember what I said about Maclaurin series. Like if you are given this series, let me share that. If you are given this series and you are given a function, if you know how to go about finding the Maclaurin expansion of any function f, given that series, raise your hand if you know how to apply it. Okay, Clary, I can see your hand. I'm waiting for others. Okay, thank you. Just wanted to be sure that we have an idea. Of course, if you still don't know how it is done, just listen to this. Okay, Christmas special. Call it Christmas special. All right. I'm gonna need you to confirm the audio. I'm sharing sound now, and hopefully, let's play this. Yeah.
Suppose we have a curve defined on a domain including x equals 0. We have previously defined the tangent to a curve as the best approximating straight line for the curve at that point. This requires the value of the function and its first derivative at that point. If we also use the second derivative at that point, we could improve our approximation for the curve using a quadratic. If we also use the third derivative at that point, we could improve our approximation to the curve further using a cubic. Using this process with the value of the function and its first n derivatives at x equals 0, we can generate the nth degree Maclaurin polynomial approximation for the curve. Since we are using information about the curve based on the point where x equals 0, we can expect any Maclaurin polynomial approximation for the curve to be most accurate near x equals 0. If we continue this process forever, we can generate an infinite series called the Maclaurin series expansion for the function. Assuming all of the derivatives exist, and that the series converges, the Maclaurin series will be exactly equal to the function. In this example, we consider a rational function.
First, does anybody understand the introduction? Is it clear to us what the introduction says? Yes? All right, thanks. Let's move on.
It is defined when x equals 0, and we can calculate as many derivatives as we like. We first write the function with a negative power, so we are ready to differentiate. The first derivative is the power times the expression to the power minus 1 times the derivative of the expression, which is 1. The second derivative is the constant coefficient times the power times the expression to the power minus 1 times the derivative of the expression, which is 1. Suppose we kept on differentiating to the kth derivative. With every derivative, we multiply by the power from the previous derivative, which will be negative. So, the sign keeps changing. It is positive when k is even, and negative when k is odd. So we write minus 1 to the power k. For the first derivative, we multiplied by 1. For the second, we multiplied by 2. For the third, we would multiply by 3, and so on. So for the kth derivative, we would multiply by k. For the kth derivative, we therefore have k factorial. With each derivative, the power of the expression 2 plus x gets reduced by 1. For the first derivative, it is minus 2, and for the second, it is minus 3. So for the kth derivative, it is minus k plus 1. For the kth term of the Maclaurin series representation of the function, we need to evaluate the kth derivative at x equals 0. Making this substitution, the first two factors are constants. and we have 2 to the minus k plus 1, which we can instead write in the denominator without the negative exponent. We also need to evaluate the function when x equals 0. Now look at the Maclaurin series formula. The first term, k equals 0, corresponds to the 0th derivative, or in other words, the function itself, evaluated at x equals 0, times x to the 0, which is just 1, divided by 0 factorial, which is just 1. So, we have the constant 1/2. The constant term of any Maclaurin polynomial is always the value of the function at x equals 0. In general, we evaluate it separately from the derivatives, so we often deal with this term by itself first. For the rest of the terms, we have the sum from 1 to infinity of our expression for the kth derivative evaluated at x equals 0, divided by k factorial times x to the k. We see the k factorials cancel, and we now consider whether we can write the first term in the general series. If we substituted k equals 0, we would have minus 1 to the 0, which is 1, times x to the 0, which is 1, divided by 2 to the 1, which is 2. So this would be the correct value 1/2 for the first term. We therefore write the series as a single summation by starting it at k equals 0. Having found a general formula for the Maclaurin series, we now consider M4 of x, which is the 4th order or 4th degree Maclaurin polynomial approximation for f of x. In this case, we take the summation from 0 to 4. We know the first term is 1/2, and we add on the terms with k equals 1, 2, 3, and 4. We then evaluate each of the coefficients, so we have a neatly written quartic. We substitute x equals 1 to find the 4th order Maclaurin polynomial for f of 1. We find it is 11 over 32. By comparison, f of 1 is 1/3, which can be written as 11 over 33.
Any questions? Is it clear to us what we've just heard? There is a way that the example was done that might be confusing to maybe a beginner. You probably don't need to go through that route. So I propose that we take a question from the book and solve ourselves. I'm sending to the WeChat group some screenshots. Let's do that first so that when I refer to a page, everybody has that page. Just a sec. So I'm sending the example also. So now I'm sending the exercise 24A, which is where the questions are. All right, so all that has been sent to us. So we're going to pick question. Let's pick question 4. Okay, actually sorry, just a sec. Yeah, okay, let's pick question, what do we do now? Let's pick for question 4. Let's derive it ourselves. Or maybe not. Derive this Maclaurin series. Let's look at question 2A together. Okay? Let's look at 2a together. So everybody write the date, whatever you normally write in your book, and write Maclaurin series expansion. Just Maclaurin series. Christmas, Merry Christmas. Maclaurin series of effects. So we already said that it's in your formula booklet also. Is f of 0, f of, I think I should write, yeah, it's okay. X comes first. First derivative at 0, x squared over 2 factorial, multiplied by the second derivative at 0, and it continues indefinitely, which you can write in some in sigma form as x to power k divided by k factorial, k starting from 0 till infinity of f to the kth power at 0. So when k is equal to 0, by this you mean zero derivative. Zero derivative means the original function itself. I think we mentioned this yesterday already. So this is what we need to remember. So for question 2a of our book, that's on page 24a, exercise 24a, page 657, exercise 24a. So let's look at question 2a. Question 2a says, derive the Maclaurin series representation. It's been given already, we just have to derive it. So 1 over 1 minus x is given as the summation. I'm writing the final answer. I skipped the middle one, x to the power k starting from 0 to infinity. So clearly, our f of x here is this rational function, which we just have to write as 1 minus x to the power negative 1. Okay, I'm not going to use the example, the approach in the example that you have just listened to. I'm going to do the derivative. So as a beginner, you might just want to do the derivative. So all you have to do is find the first derivative. So let's do that together, please. Our first derivative will be minus 1, right? 1 minus x to the power minus 2 multiplied by minus 1, right? Okay, and which will be minus 1 is gone, so just 1 minus x to the power minus 2. Our second derivative will be minus 2, 1 minus x raised to the power minus 3, then also times minus 1, right? And that also cancels, that's minus cancels minus again. So we have what? 1 minus x to the power minus 3. Our third derivative is going to be minus 3, 1 minus x to the power minus 4, then times minus 1. So that's simply, oh, I missed something here. That would be 2, right? 2, 1 minus x to the power minus 3. So this will be 3, 1 minus x to the power minus 4. And it continues like that, right? So when you substitute, I don't have enough space. when you substitute x is equal to 0, this implies that f prime at 0 will be 1 minus 0 is 1. 1 raised to power anything is 1. Do you agree? Talk to me, guys. Agreed? Okay. When we substitute this, second derivative at 0 will be 2. I'm skipping what I'm supposed to write because of the space. Okay, so please just do some computation. Just show one step before the answer. Understand? Clarissa? You look confused. Do you understand?
For the third derivative, do we have to put the 2 into, would it
2
be
and 2?
negative 6 instead?
Oh, sorry, 3 times 2. My bad, my bad, my bad. Did you guys see what she's talking about? Remember, it's going to be 3 times. So it should be, wait. This is minus 2. Yeah, this is correct. Then for this, third derivative will be 2 times that. Okay, I missed that, sorry. This is why I need you guys to be part of my workings, okay? 1, 2, 3 of x. So there will be 2 times minus 3. Yeah. So 1 minus x to the power minus 4. And that will be 6. Okay, so you don't have to write it as 2 times 3. Just write it as 6. There's a minus 1 also. Okay, there's a minus 1 also. So everything becomes 6. 1 minus x to power negative 4. Is that okay now, Clary? So third derivative at 0 will just be 6. And these are factorial numbers because if you look at the fourth, the expansion ends at x to power 3. You can also always write up to 4, which is fine. So therefore, by the Maclaurin series expansion formula, okay, therefore, so I'm just going to say from f of x equals summation f to the kth derivative at 0, k starting from 0 till infinity, x raised to power k over k factorial. It doesn't matter which of these comes first. It implies that 1 over 1 minus x. Now, f at 0, we haven't done that. So this will be here. F at 0 will just be 1, right? Yes? Okay. So this is 1. The second term will be x and first derivative. Guys, hold on. Do you prefer this or you prefer this? Or it doesn't matter? I need you to turn on your mic and talk to me, please. Do you prefer this or you prefer this, or it doesn't matter for you?
Both are fine.
Anyone has a preference? No? Okay, so let's move on. So if I'm using this now to do my substitution, x, the first derivative at 0 is 1, and x squared over 2 factorial, 1 also. No, that's 2. Okay, that's 2. Then I have the third derivative over 3 factorial times 6, and it goes on. So clearly, this is 1 plus x, 2 and 2 factorial cancels, 6 and 3 factorial cancels, and it continues like that, which we write in summation form as the summation of x to power k, k starting from 0 to infinity. And that's all you are asked to show. Okay, because you will observe a pattern. So you should learn to write it in summation form. Can I ask you to try 2b? Okay, question 2b. You can check the we tab. I'm going to write it on the screen here. So question 2b is this. You are to derive the Maclaurin series expansion of the natural log of 1 plus x, and it's supposed to give you k from 1 to infinity, and the numerator here is minus 1 to power k plus 1. Everything over k, then multiply by x raised to power k. Okay, can I ask you to do this within 5 minutes, please? You can check your screenshot. I sent that to you already. So I'll just leave this on the screen while you do that. I'll pause the recording also. Please take just 5 minutes to make the attempt, then we can do it together again. Okay, so I've resumed my recording now. So let's do question 6 together from the book. You have the screenshots. So question 6 says, I share that first. This one. Oh no, not this one. Question 6 says, show that sine x is that series. Explain why there are no second order polynomial, Maclaurin polynomial in this case. What feature of sine x has caused this? Also, find m5 of x, which is the series up to the order 5, that is up to power 5. Compare that with, compare m pi over 6 with sine pi over 6, which is half. So let's quickly do this together, quickly. Okay, can I have everyone's attention, please? Some seems still doing something, looking down. So please, let's do this, and I want everyone to be part of this. So question 6. Question 6 of page 657, exercise 24a. The first question is for the Maclaurin series of sine, which is in our formula booklet to be derived. So let's derive it ourselves. So all you have to do is assign f of x to be sine x. Find f prime of x. Together, what is that, please? I need people to talk to me quickly. Guys, come on, come on.
Cos x.
Cos x. So please turn on your mic and be part of this discussion. The second derivative will be
Negative sine x.
negative sine x. Thank you. We're going to stop at the fifth derivative because of c. Okay, because of c especially. So the third derivative will be waiting.
Negative cos x.
Negative cos x. And the fourth derivative will be
Sine x.
sine x. Because that would be minus minus sine x. So that's a sine x. And the fifth derivative will be cos x again. So from this, we can find f of 0. This is sine 0, which is 0, right? So at 0, f prime will be cos 0, which is 1. The second derivative at 0 will be minus sine 0, which is 0. The third derivative at 0 will be minus cos 0, which is negative 1. The fourth derivative at 0 is sine 0, which is equal to 0. The fifth derivative at 0 is equal to cos 0, which is equal to 1. So therefore, f of x, which is equal to f at 0 plus x, that x squared over 2 factorial I like to state it. It helps you remember and so on. Will be, instead of f of x, you write sine x. It was never called f of x. You call it f of x while working on it. So sine x will be, the first is 0. Some of you didn't include it. I will appreciate if you include it at least in the first time. Okay. Then x times 1, x squared over 2 factorial times 0 again. Then x cubed over 3 factorial times minus 1. x4 over 0 over, sorry, 4 factorial, sorry. What is that? Times 0. Then x5 over 5 factorial times 1, and so on. So clearly, this cancel, all the zeros won't cancel, so you are left with x minus x cubed over 3 factorial plus x5 over 5 factorial. Definitely the next would be minus x to the power 7 over 7 factorial, and it continues. And clearly this will be sigma, because this is x to the power 1 over 1 factorial, isn't it? Right? Callista, you're not paying attention, and I do not like that. I expect everyone to listen and ask me questions, help me discover mistakes. But I don't know what you're typing on your iPad and you're looking down, and that is not going to help you. So let's try to get the sigma notation format. So like I said earlier, so I'm going to repeat that. Others looks like power and factorial. So this will also be power 1 divided by 1 factorial. Just so we can see it clearly. So you could see that the powers are what type of number? Anyone? And the factorial also is a factorial of what type of number?
Odd number.
Odd number. So the format of an odd number is either 2k plus 1 or 2k minus 1, right? So you have that in mind. Also, you have a alternating series, plus minus, plus minus. So definitely you are dealing with a minus raised to power some k or some k plus 1 somewhere. Now, some k or some k, sorry about that, some k or some k plus 1. So we can have k plus 1 or k minus 1, it doesn't matter. When k is equal to 1, now our k will be starting from 1, I think. Yeah, we don't need 0 because we don't have a 0 factorial. Or we can look at the format that the question wants. Okay, the format wanted is when k is equal to k raised to power k from 0. So let's check. When k is 0, you have 0 plus 1. In that case, we have to change it. So this will have to be raised to power k. When k is equal to 0, anything raised to power 0 is 1. It's gone. When k is 1, you have a negative, which is this. When k is 2, you have minus 1 squared, which is this. Okay? Hello? Understand? So you have to fix the sign first. After you have fixed the sign, you could see clearly that this is x raised to power something over something factorial. Now, when k is equal to 0, you want 1. Because it's odd number, so it's likely this or this. So check which one gives you 1 when k is equal to 0. That will be the first one. Okay? Hello? Okay, so when k is equal to 0, that's what you have. So, and that looks like what, let's see. If you have 2k plus 1, when k is 0, when k is 1, you are going to have 3. Yes. When k is 2, you are going to have 5. Yes. So this is going to be 2k plus 1 factorial as well. But that seems to be different from what we have, is it? Oh yeah, it is. I was looking at something else. I was looking at that of cosine. Okay, so this is it. So you can write in this form, or you could write, the negative with the first one at the top. I'm going to write exactly the way it is given in the required result. Now we have seen it. So you have a fraction minus 1 raised to power k. You have 2k plus 1 factorial, and you have x raised to power 2k plus 1. If the question had said up to infinity, of course, if it was saying k from 1, then this will change. Let's put that by the side. It's not the requirement in this question, but in case you come across that in subsequent question, let's write it in the format of when k begins from 1. If k begins from 1, let's see. Clearly, our sign will be minus 1 raised to power k plus 1. Because when k is equal to 1, you're supposed to have 2, isn't it? Which will make this positive. Okay, so there will be like a shift of plus 1, basically. Okay, but we don't have to shift this. How do I get an odd number when k is equal to, I want to have a 1. So you remember, you can write odd number in 2 ways, like this or like that. Right? You can have 2k plus 1 as odd number or 2k minus 1 as odd number. Please, I need a confirmation. You can just nod your head so I understand what you're saying, what you mean. Not just total blank, no reaction, please. So clearly, this will be our the sign, and this will be the odd number to be used, not this odd number format. When k is 1, this will be 1. When k is 2, this will be 3, which is what we need. So if the result wasn't k starting from 0, if it was starting from 1, then this is the answer that would be expected of you. Minus 1 raised to power k plus 1, or even k minus 1. That could be used as well. Okay, raised to power k minus 1. Then this would be 2k minus 1. Excuse me. This will be 2k minus 1 factorial, everything raised to power 2k minus 1. Whatever you have here is what you have here. Okay? The same results could be, talking about the one in red, k from 1, minus 1 raised to power k minus 1, and you have 2k minus 1 factorial, then x raised to power 2k minus 1. This is up to infinity. So, but because the question is already given, okay, it's already given in this form, like show that it is this, that's why you stop here. But if it wasn't given, all these three will be acknowledged. All these three will be given. Okay, now B part of the question says, explain why there are no second order Maclaurin series in this case. Yes, who wants to go first? Raise your hand. Let's start with Krista C. Yeah, so we can save time. I'm picking. Krista C. Do you even understand what they mean by second order Maclaurin polynomial in this case? Krista.
Does that mean the second derivative?
Not just that. Why do we, yes, that second derivative, or even the second, the even derivatives, if I may use that. Like the even powers do not exist. X squared is gone, x to the power 4 is gone, x to the power 6 is gone. Okay, that's what it means. Yes, you are right. So can you tell us why we do not have that? What feature of sine x has caused this, Krista?
Because sine x will turn to be cos x.
Say that again.
Sine x will turn to be cos x.
No, sine x is cos x at 45 degrees, which is pi over 4. I think you're thinking too much. It's something simple. Maybe you're thinking it's something huge. Okay, Callista, your turn. Nice one, Krista. Let's ask Callista. Yes?
So when x is equal to 0 and sine x, it's going to equal to 0?
That's it. Because at 0, sine x is 0. Sine x crosses the x-axis at 0, among other points. Okay, so that feature that sine x touches the origin causes all this mess in quotes. Okay, now The next one is find M5. Okay, find M5 and compare with this. So M5 means the Maclaurin series expansion up to when n is equal to 5. Am I making sense? Which is these three, basically. Okay, find M5 and compare your M5, compare M5 of that to that. So let's see quickly from 0 to 5. Let's go to the next page. Okay, so the B part, do not forget. Okay, second order does not exist. Since sine x is equal to 0 at x is equal to 0, that's enough. Okay, that's enough. C. If you have any other additional information, you can include and explain, but it's as short as that. So M5 of x means the Maclaurin's expansion of f of x, okay, up to that. So that will be when from k from 0 to 5, from 0 to 5 of what is this? The general formula of this. So basically, you are copying and pasting this and changing this to 5. That's all. Okay, that's all. It's something you have done. So you're just changing infinity to 5. So let's write that. Minus 1 raised to power, oh, it's in the book. So I just take it from here. Minus 1 raised to power k. You have 2k plus 1 factorial. Then you have x raised to power 2k plus 1. Okay, so k from 0 to 5. So if you write it, you expand this using your knowledge of sigma notation, or you can just copy, just copy these 3, right? You just copy these 3 because 2 are missing. No, are they the ones missing? 2 are missing. No, are they 2? This is meant to be 6 terms, so 3 are missing. So basically, you have x.
Wait, Mr. Daniel?
Yes, please.
Then wouldn't it be k to 2? Like k from 0 to 2?
No, what do you mean?
Because it goes to x to the power of 5, right?
For you to get x to the power of 5, your k has to be 5. Oh, wait. Oh, no. Sorry. So thank you, Lillian. True. You need your degree to be 5. So it's not from k to 5. My apologies. So it's going to be up to 2. My apologies. And that is how you get this one. You need your power of k to be 5. You're talking about order 5. Okay, Maclaurin series up to order 5. So that will be your sigma k from 0 to 2 indeed. I'm so sorry. I totally forgot that the power is not natural numbers, but odd numbers. So for you to get your 5, you have to stop at 2. Thank you, Lillian, for that. Okay, this is why I need everybody to pay attention in case I skip something, I miss something. Now, from this, you are supposed to compare M5. So I need your calculator now of pi over 6. So which will be pi over 6 minus, not plus. Okay, I got a message. Who's that?
I calculated it.
Calculate what? Okay, you need to be part of this first, then you can tell us that. So this will be 3 factorial. Okay, Mr. Chang, I need you to observe this with me in case I made a mistake. Then 1 over 5 factorial, something like that. Is that what you sent, sir?
Yeah.
So can you tell us that again? 0.5
0 0 0 0 4 zeros.
Okay, then
2 1.
say that again.
2 1.
Like that. So you are supposed to compare that with sine pi over 6. Okay, why are we comparing with sine pi over 6? Remember, this is the expansion of sine. Okay, up to the 5th degree. So sine pi over 6 is just 0.5. So if you look at it, it's a good approximation indeed. Okay, find that. That's what we have just found and compare with this. So which is very close to what that will be. Okay, moving on. There are more questions we will try on your own later from the book. I want us to look at the composite functions when it comes to Maclaurin series. This I also explained yesterday, but let's just quickly look into that. Composite functions. Maclaurin series of composite functions. As you know, when we talk about composite function, we're talking about combination of more than one function, right? It's not just a function, there are two functions included. So we're going to, I think I play you an example. Actually, there are two examples. I'll play that just to save time. Then we can take an example together in the class as well. Before you, I'll be sharing this with you later if anybody needs. Just a sec. The composite function can be found in section C of that chapter 24, by the way. I'll send you screenshots also later, so don't you worry about it. So let's play this. The first one is, what is this one? Okay, it's not this one. All right, almost. Give me a thumbs up if you can add the audio.
We have already seen the summation notation definition of the Maclaurin series. It can be used to generate Maclaurin series representations for a number of standard functions. Depending on our purpose, it may be more appropriate to use summation notation or simply the first few terms. Notice that each of the series has an associated interval of convergence. For values of x within that interval, the Maclaurin series converges exactly to the value of the function which it represents. Notice that the Maclaurin series for 1 plus x to the power p is exactly equivalent to the expansion from the binomial theorem. A list of common Maclaurin series like this is useful because we can use compositions with another expression to generate other infinite series representations for functions. Note that the series we generate will only converge if the interval of convergence of the original Maclaurin series is obeyed. The infinite series generated will only be a Maclaurin series if it is a polynomial. In this example, we are given the Maclaurin series for 1 over 2 plus x. To find an infinite series representation for 1 over 2 minus x squared, we substitute minus x squared in place of x. Using the index laws, minus x squared to the k is minus 1 to the k times x to the 2k. Minus 1 to the k squared is minus 1 to the 2k. We cancel this factor because minus 1 to any even power is just 1. We substitute k equals 0, 1, 2, and 3 to generate the first terms of the series until we reach the power x to the 6th. Since the series we are generating is a polynomial, it is in fact the Maclaurin series for 1 over 2 minus x squared.
Understand that? Yes? Talk to me, please. Yes? All right. Let's look at this. This is another composite function. If there is anything mentioned there that is not clear to us, please speak. Can you see
In this
another one?
example, we demonstrate the use of composite functions with Maclaurin series to generate further Maclaurin series representations. We will make use of a list of common Maclaurin series. In part A, we begin with the Maclaurin series for e to the x. To generate an expansion for e to the 2x, we substitute 2x in place of x. To generate an expansion for e to the 4x, we substitute 4x in place of x. To generate an expansion for e to the nx, we substitute nx in place of x. In part B, we begin with the first few terms of the Maclaurin series expansion for cosine x. If we want, we could also use the summation notation form, but we will come back to this in a minute. To find an expansion for cosine e to the x, we substitute e to the x in place of x. Notice that there is a constant, and then exponential terms of the form constant times e to the nx, exactly as we generated in part A. Suppose we substitute for e to the 2x, e to the 4x, and for some general term, e to the 2kx. Notice how we replace n with 2k in our formula from part A. We are only interested in the first two non-zero terms of the expansion. The first of these will be a constant. It is 1 plus the constant term from the expansion of minus e to the 2x over 2 factorial plus the constant term from the expansion of e to the 4x over 4 factorial, and so on through all of the rest of the infinitely many terms. So, we summarize the constant as 1 plus the sum from k equals 1 to infinity, and use the constant from the general term involving e to the 2kx. The next term will be the x term, and again we need to collect the x terms from each of the expansions of the exponential terms. We summarize these in summation notation as the sum from k equals 1 to infinity, and use the coefficient of x from the general term involving e to the 2kx. All of the rest of the terms in the expansions involve higher powers of x. So, we have written the first two non-zero terms, and we can now remove the brackets, and in the coefficient of x, we can cancel 2k in the numerator and denominator. As promised, we can also generate these terms by starting with the summation notation form of the Maclaurin series expansion for cosine. To find an expansion for cosine e to the x, we substitute e to the x in place of x. We now want to use a series for e to the 2kx. We get this from part A, but we need to be very careful with the counters we use. We already have the counter k for the cosine series summation, so we now use the counter j for the e to the 2kx series summation, and we substitute this in. We swap the order in which we do the summations. We can do this because it simply means we are adding the terms in a different order. The first two terms in the expansion correspond to j equals 0 and j equals 1. The k equals 0 term from the first summation is the one we saw from the other method, and the rest of that summation is the same. We cancel 2k in the numerator and denominator of the second summation, and this matches the x term from the other method. Now look at part C. For x close to 0, x squared will be much smaller, and x cubed will be even smaller, and so on. So, for small x, we can use the first two terms as an approximation for cosine e to the x. Look back at the question, at what we need to show. To show this, we need expansions for cosine 1 and sine 1. To get these, we can use our known Maclaurin series for cosine and sine. We substitute x equals 1 into the series for cosine and into the series for sine. Now compare the constant term in our expansion for cosine e to the x with cosine 1, and the coefficient of x in our expansion for cosine e to the x with sine 1. We conclude that for small x, cosine e to the x is about cosine 1.
Sorry.
Now look at the coefficient of x in our expansion for cosine e to the x with sine 1. We conclude that for small x, cosine e to the x is about cosine 1 minus sine 1 x. Finally, in part D, we calculate the second degree Maclaurin polynomial approximation for cosine e to the x. This is the best approximating quadratic for the curve at x equals 0. We let f be the function cosine e to the x. To find the first derivative, finally, in part D, we calculate the second degree Maclaurin polynomial approximation for cosine e to the x. This is the best approximating quadratic for the curve at x equals 0. We let f be the function cosine e to the x. To find the first derivative, we apply the chain rule. The derivative of cosine is minus sine, x equals to the x, times the derivative of e to the x, which is itself. To find the second derivative, we need the product and chain rules. We start with the derivative of minus sine e to the x. Since the derivative of sine is cosine, we have minus cosine e to the x times the derivative of e to the x, which is itself, and we multiply this by the second factor, e to the x. Then we add minus sine e to the x times the derivative of e to the x, which is itself. These e to the x for m2 sine e to the x degree Maclaurin polynomial.
Because we're just hearing the voice, we are not seeing the picture in real time, but I believe everyone knows how to differentiate using product rule. Okay, so that's why I'm skipping that, because it was beginning to get boring if we can't see what is being said. So this is just product rule, and when you substitute, you get that. So let's hear the concluding part.
The constant term is just f of 0. Then we have f dashed 0 over 1 times x. Then we have f double dashed 0 over 2 times x squared.
You see, even the last time has been said, but we cannot see it. Finally, it's coming out. I don't know why they have that. Well, nothing is perfect in technology. I know this is a long question. I will send you the screenshot. Take your time to look at it. Before we go, I'd like to also show, this is composition. There are questions to be done under composition, which I will be sharing with you. So this is the one we have just looked at. These are composition problems. And if you look at the, did I send you Maclaurin's past questions compilation? Did I send that already? Guys?
Yeah, I did.
I did?
Yeah.
I think you sent yesterday.
All right, so please look into, you will see how some of this can be used. Like I said, when we come back to school in our first week, we will do a review of this. So I'm sending this. I don't want us to waste time doing any practice here. Now, this is another one that you should know. Addition and subtraction, no big deal. Again, use this to write the terms of this. All you have to do is put them side by side, that's all. Hello, am I making sense? Use the Maclaurin series of this and this to write the series of this and this. All you have to do is put them side by side. However, you're going to need composition here. Can you see that? Because you have sine x. Now they're talking about sine x squared. So you need to get sine x squared, get cos 3x from cos x, and do your subtraction. That is the addition and subtraction. That's all it's about. Even your textbook did not put any example because I believe they probably think it's too trivial. We have something called hyperbolic function, which is not in your syllabus, but you don't need to worry. The hyperbolic sine function is given as this. Show that the hyperbolic sine is this. So all you have to do is use your Maclaurin series. Again, you have the series for exponential x. You find the series for exponential minus x by just replacing x with minus x in this. Understand? And then you subtract them and everything is multiplied by 1/2. And you should be able to come up with this. Similarly, you can do the hyperbolic cosine function for x using Maclaurin series. And here, this is your Euler formula. You can always get for E minus theta. So basically, you just substitute. We use this in Form 5 to generate it. So now they are saying by separating the series into real and imaginary parts, prove this. So it's the same, is exactly what you proved in Form 5. They're asking you to prove now. So you might want to try that on your own. So I'm going through this in a rush. Please take your time to look through them. Differentiation and integration. You can also use differentiation and integration to get Maclaurin series expansion. Look at this. The Maclaurin series for cosine is this. By find the Maclaurin series for sine by differentiation. Look, if you differentiate cos, you get minus sine, right? Differentiate cos, you get minus, or maybe I play so we can hear the explanation, or maybe I just run through it myself. Let's play that. Because there are some additional information that comes with some of this explanation, which I may not put. So if I didn't include that, at least you can hear more information from the explanation given. So you will only be required to use differentiation or integration when the functions are related by derivatives or integral. Like you would never be asked to find the Maclaurin series expansion of cosine by assuming the Maclaurin series for exponential x, like they are not even connected. Understand, everyone? Okay, so let's play this quickly. This section will be the last I'll show you for today. Because I want everything to end tomorrow, so that's why I'm rushing through this.
We already know the sine function is related to both the derivative and antiderivative of the cosine function. In this example, we see how these relationships are observed between their Maclaurin series. Since Maclaurin series are polynomials, we can differentiate and integrate them term by term. This is particularly useful when we differentiate or integrate in summation notation. In part A, we know that the derivative of cosine x is minus sine x. So, sine x is minus the derivative of cosine x, and we substitute the given Maclaurin series for cosine x. The series for cosine x converges for all real x, so this expression for sine x must also converge for all real x. When we differentiate a Maclaurin series, we need to be careful with the first term. We will see why in a moment. In this case, when k equals 0, we have the first term minus 1 to the 0, which is 1, over 0 factorial, which is 1, times x to the 0, which is 1. So the first term is 1. We keep the rest of the series in summation notation. When we differentiate term by term, we have the derivative of the constant, and then we have a sum of terms which have the form of a constant times the derivative of x to some power. The derivative of the constant is 0. We remove the negative coefficient.
I hope everybody understands what has been done here. First of all, notice that the sigma notation was starting from 0 here. Now it changes to 1 because the first one has been removed. That's first. Second, when you're differentiating term by term, so the derivative of a sum is the sum of individual derivatives, right? Derivative of sum of terms is the same as the sum of individual derivatives. That's what has happened here. So derivative of this sigma is actually the sigma of the derivatives. And we all know that this is a constant, right? So usually constant is separated while the derivative is going on. So that is the reason for this. Okay, it's things that we have done, just that it is being written in sigma notation.
Of the summation and add 1 to the power of minus 1 instead. And we use the rule for differentiating x to a power. We cancel 2k in the numerator and denominator. This is the moment where it is important that we took out the constant term. We know its derivative is 0, so we have cancelled it. If we had left it in the summation, then at this moment of cancelling 0 over 0, we would be left with a first term in the derivative, which would be minus 1 over minus 1 factorial, which we have no definition for, times x to the minus 1. At this point, we now want to write the series for sine x as a summation from 0 to infinity, so it is in the familiar form. We therefore let a new counter n be k minus 1. Changing counters is a very useful and important tool, but we need to do it carefully. K equals 1 corresponds to n equals 0. K being infinite means n is infinite, and we replace every other instance of k with n plus 1. We now tidy the expression. Minus 1 squared is just 1, so we can take 2 from the power of minus 1, and we can expand some brackets. We are left with the familiar form for the Maclaurin series for sine x. In part B,
Does this make sense? Yes? Hello? Okay.
we know that the antiderivative of cosine x
That's
is
by
sine
integration
x.
now.
Now, if we just integrate cosine x, we need a constant of integration. We would then need to evaluate that constant using a known value of the function. For example, sine 0, which we know is 0. One way we can incorporate this constant from the beginning is to apply the fundamental theorem of calculus. If we take the definite integral from 0 to x of cosine t dt, we will have the antiderivative sine t, and this will give us sine x minus sine 0. And we know sine 0 is 0, so we are left with just sine x. So, we replace cosine t in this integral with its Maclaurin series. And then to integrate term by term, we move the integration inside the summation. To integrate a polynomial term, we have the coefficient, we add 1 to the power of t, and we divide by the new power. We can tidy the denominator by including the factor 2k plus 1 in the factorial. We evaluate the antiderivative at t equals x. Then when we take away the antiderivative evaluated at t equals 0, we see every term in the summation will be 0. So, we are left with the familiar Maclaurin series for sine x.
Is this clear? So what I want you to do, I'm sending you screenshots. I'm not going to assign any homework. I'm sending you screenshots of all the pages. We have to wrap up this in about 5 minutes. I still have about 2 examples from the book. I will send you their screenshots also, because we don't have time to play it yet. So they're probably going to be the first example that we play. Then we go to division and multiplication also tomorrow. Then numerical. There is an aspect of differential equation that I skipped because we haven't done Macnolia series. So then we will be able to do that. Let me see if I can find that. It is called Maclaurin series developed from differential equation. So 3 things I want us to be able to do tomorrow. The question on multiplication and division is just the way we did addition and subtraction. Okay, then we look at some example. I'll send you the screenshot. Please feel free to. Maclaurin series is done. We're just looking at different areas of questions, of likely questions. So please look at your worksheet also. If you have some time, nothing will be assigned today. It's Christmas. You shouldn't even be here in the first instance, but I really appreciate you coming. So we will start by playing this video to add some of these examples tomorrow and take some examples on our own from the board. Any questions before we close the class? No? Please, if you have any question, please send to me. Please take some rest if you must. Even if you do not open anything before tomorrow's lesson and I ask you a question you can't remember, I will be cool with it. But if you are able to, please go for it. Okay? Thank you so much and see you tomorrow. I'll send some screenshot now and I will share the video also later if you want to watch, especially some of those complex examples. Bye.